Hey guys, this is going to describe to you what the difference between a molecular formula and an empirical formula is. You guys already know about empirical formulas. These are things like carbon dioxide and water. We know it's the simplest, the lowest whole number, simplest mole ratio of the elements in a compound. So carbon is a 1, oxygen is a 2. It's a 1 to 2 ratio. Oh, by the way, I should probably identify that it is me doing this, not you. You don't have to do that. Anyway, so let's take a look at what an actual, the molecular formula is. It is the actual numbers. It's not the lowest whole number ratio. It's the actual numbers that are in the chemical structure, because some chemical structures are pretty darn big. And the empirical formula is almost like it's the actual one reduced down. Let me show you an example. Okay, if we have a molecule here, boron trihydride, that is the empirical formula, but this actually forms as a dimer. That's what it's called. And it actually forms like this, B2H6. So technically in the actual molecule you have 2 borons and 6 hydrogens, but the empirical formula is the lowest whole number mole ratio. So 2 and 6 get reduced down to 1 and 3. And this, of course, is also reflected in the molar masses of the two. If we find the molar mass of the empirical formula, BH3, boron is 10.79, and we have 3 hydrogens at 1.01, so that's 3.03. So that's a total of 13.82. Now let's do the molecular formula molar mass. B2H6. Well, that's 2 borons, so that comes in at 21.58. And then hydrogen comes in at 6 of them, 6.06. Do that math and you get 27.64. Now, if you divide 27.64 by 13.82, what does that end up being? 2, because the molecular formula is 2 times bigger than the empirical formula, which was reflected here. 2 borons, 1 boron, 6 borons, 6 hydrogens, 3 hydrogens. So again, the molecular formula is reflected twice as big as the empirical formula, just like the formulas actually were. Now, one of this that's a really common example you'll see is glucose. Remember, that's what's used in the mitochondria to get broken down so we have energy. It's C6H12O6. Well, what would the empirical formula be of this if it's a whole number ratio, the lowest whole number ratio? Well, you can reduce this down to C1H2O6. And again, if you do the molar masses of these two, the empirical molar mass is 30.03 grams per mole. And the molecular molar mass is 180.18 grams per mole. So, how many times bigger is the molecular molar mass than the empirical molar mass? 6 times. Just like, I have to erase something. I'm sorry. That is actually a 1 here. Sorry, my bad. There we go. CH2O. It's 1H2, 1, and 6, 12, 6. Sorry about that. But again, this is the most reduced form, and this is the actual. Okay. Now let me show you kind of how to use this. Let's say we want to determine the molecular formula, so that's what we're looking for of a compound. With the empirical formula is CH, and the molar mass of the molecular formula is 78.11. Well, let's look at this. So the first thing we're going to need, if we have the empirical formula is CH, if we can calculate that molar mass, divide it into this one, we can see how many times bigger the molecular formula is than the empirical formula. So first, let's get the empirical formula molar mass of CH. That would be 12.01 plus 1.01 is 13.02. And then how many times does that go into? Right here. Well, that goes in 6 times, roughly. And so since it goes into there 6 times, that means the molecular formula is 6 times bigger than the empirical formula. So that means it's C6H6. And that's the molecular formula. Again, it's 6 times bigger, and how did we find that? We just compared the molar masses. Next example. This one is giving you how much hydrogen and how much oxygen. But it's not giving the empirical formula. It's giving the molecular molar mass. Again, that's the molar mass of the molecular formula. But we don't have an empirical formula, so what do we have to do? Find the empirical formula. And we do that by, yep, you guessed it, divide by the molar mass to get moles. Go ahead and set this up too. And now we go ahead and we need to do the calculation here, which, sorry, I'm opening up my phone to get my calculator because I didn't come with my normal calculator. So 0.44 divided 1.01 is 0.44. And let's do the other one. 6.92 divided by 16 is 0.43, but essentially that's a 1-to-1. So we know that the empirical formula is HO. Ho ho ho. Okay, so now we have to find the molecular formula. So our next step is to find the molar mass of this. Well, hydrogen is 1.01. Oxygen is 16.00, a total of 17.01. Well, how many times will 17.01 go into 34? Well, 34 divided by 17 is 2, right? And so that means the molecular formula is 2 times bigger than the empirical formula. So what's the molecular formula? Yeah, you got it. H2O2, which you probably remember back. We've dealt with this a lot. This is what again? Hydrogen peroxide. Okay, so again, this is how you're going to find molecular formulas from empirical formulas. What I'd like for you to do is, if you flip this over, I can't remember how many problems there are, but go ahead and give those a try. There's kind of like examples of both types of problems. All right, good luck.